The last day of EuroBSDcon 2014. Our next speaker is Masao here, who will be telling us a few things about some useful tools supporting to the BSDs. So take it away.
Hello, thanks for attending. My name is Masao Uebayashi, coming from Japan, and I'm self-employed. I have my own company doing BSD, hopefully BSD development, and now I'm working for a customer who is developing network firewall product based on OpenBSD, and their business is really good, and they are developing good product and extending OpenBSD, and they have some local extensions, including networking related daemons, and it works. But they also had experienced some problems, and especially memory leakage, because networking daemons run for a long time, and it's coded, but if it's coded battery, it's slowly leaking memory, and it ends up with severe problems. And they wanted to fix it, but finding those dynamic memory leakage is very difficult. And actually, there are not so many options to find those memory leakage, memory debugger. So they decided to port Berglund, which has already proven its usefulness and found many problems in Linux. And so porting, previously people already ported Valgrind. It's not really used widely, but they have ported, and it is said to be working. But if there is still a big uncertainty if it really works on OpenBSD, because OpenBSD has many local features to make it more secure. But my customer is very good, and they are generous, and they allowed me to work on this uncertain project. So, and my porting project is not really finished, but I have reached to a point where I can finish this project. And so I want to show you first that it's really working, and it's real. Sorry. Has anyone tried Berglund for OpenBSD? No. Okay. It's not really. No. I think some problem. It worked 30 minutes ago, but just give me for 1 minute. Zero.
Isn't it 22.1?
20.
Can you fix the network?
Right.
You can't probably break it.
2, 1, 2.
Yeah, I can.
2, 1, 1.
No, I can.
Ah. If you tell us the password. You can log in.
Anyway, I think I can show you later.
It's a Mac, so you can probably use the desktop to get the name.
It's very close, just from there, but it's a little difficult for now. Anyway, so I suppose all of you already had the name of Valgrind, and you already know how to use it vaguely. It's basically most known as a memory profiler, memory debugger, and actually it has more features internally. But for now, I'm already working for porting memory profiler, and porting all of them is a little too much work, and it's basically for developers because it helps development, and actually it can run unmodified programs. So we can use it, just users can use it, but it does not help to accelerate watching movies, something like just slow things down, so it's not really helpful. And Berglund work is not finished, and it still has bugs. So if you want to use it now, you have to debug Berglund. That is not fun, but still I need some help from you to stabilize and detect. So I don't want you to involve Berglund development deeply, but still. So I need some help from advanced users.
Okay, bye-bye.
Sorry. So I set 3 goals in this presentation part is involve more people and explain its internal, and I want to focus especially 3 things, that is syscall, system call, and exactbe. When Berglund executes a debug target program, it internally does what kernel does for exactbe. So Berglund has to simulate what kernel does in exactbe, and it has also to simulate a signal, which is very fun. ideally, Berglund can work without any fixed changes against NetBSD or OpenBSD locally, but unfortunately, I have found some changes to be done, so I have to convince community to accept those changes. So you can see this explanation at the official site of Valgrind, or their papers, that Valgrind is a framework for heavyweight dynamic binary instrumentation, which is a little too difficult to understand for me. And you can also see Wikipedia, and it says it's essentially a virtual machine. So this is much easier to understand, and in my opinion, it describes the things more correctly. So it's basically a virtual machine and the emulator. And once it starts to start running, what it does internally is basically a loop which interprets client debug code and disassemble it and execute those instructions one by one. It's basically what it does. And instead of actual registers, it has virtual registers in memory. So if you see some move instruction which moves value from one register to another, what it does is just copy that value in virtual CPU. This is the basic. This is another view. Berglund is special in that it executes debug targets within the same address space. It's one process. Berglund runs somewhere in one process address space, but still target client, target program is mapped in the process, in the same process. This is very special for Berglund, I think. And but still, actual stock given by kernel is used by Berglund by itself, and client stock is allocated somewhere else. So slightly for clients, it's basically the same. It does not know if it is executed in Berglund or not, but still there is some difference. You can see many documentations and papers at berglund.org, and which is good. And my project is based on FreeBSD ports hosted at Bitbucket, and I could just fork that branch. Okay. This is our view, static view, how their code is structured. In essence, Berglund is emulator, and they have emulator code, which is very portable. In that, actually, I had to change no code in the central core emulator. It's called Vex, I had to change nothing about it and except some basic type definitions in headers, but it is written in portable way. And it also has to interact kernel to do many realistic things like system call and signal or something like that. And to port Berglund, I had to modify those parts, which I'm explaining. And actually, those resources Valgrind project provides papers are all about emulated and theoretical parts. And realistic part, there is no documentation. That is the problem. So there is some numbers, many machine-dependent files, and if-defs. So they have some definitions for if-defs. I can see on. You cannot expect quality of code like BSD. This is a typical example. They have in single.cpy, you see one if-def VZP. P means platform, and x86 Linux specific coder, like this, and AMD6 for Linux, like this, and like this. So this is not beautiful, but it works because they already have you see error burn. This one, if you forget to add your platform definition, you see compilation error. So this is not beautiful, but it helps to do development. So if you port Berglund, just get used to it. Valgrind is basically developed for Linux originally, but it's ported and ported for Darwin and Android, which is almost Linux, and the Darwin code is already merged into their official branches. And as I said, there is a FreeBSD ports, but unfortunately it is not merged into the official branch. I don't know the reason, but their page declares that FreeBSD port is maintained out of tree, which means they don't intend to merge FreeBSD code. I initially wanted to merge my work, NetBSD, FreeBSD ports into the main tree, but I have changed my mind, and I think we can maintain our changes as external port. as far as we don't want to extend the basic functionality, just maintain for it. And now we have good version control systems like Mercurial. It is doable. So I think I'm happy with maintaining ports in Bitbucket project. My work is kind of between alpha quality and beta quality. At first, of course, it didn't work at all. Like I'm calling initial development stage, and after that, some limited, most simple programs start to work. But at that time, you still had no idea if test code had bugs or Valgrind had bugs. So you see some problems. You have to debug both things. And Berglund is basically a debugger, but if debugger has a bug, it's very confusing and it's not really fun. So I'm now trying too hard to make the situation from here to, and knowledgeable developers who don't know Berglund can test and help. Yes. No. So I want to explain system call. Actually, Berglund has to simulate system calls, so I have to understand system calls to simulate it. And system call from our user application point of view, it's a C function. But internally, it's okay. This one example is this OpenBSD's lead system call. If you call us lead system call from your code, it's just C function and jump this here. And internally, there is a queue of instructions, and real system call instruction is here. This is mmap. It has more arguments, so a little more code. And basically, from kernel or from CPU, system call instruction is just one of traps or exceptions. And when application code is running, and it gets hardware interrupt, CPU and the kernel tries to save all context registers into some areas called trap frame. And after CPU finishes those tasks, it just restores those information back into CPU and just returns back to application. And applications does not notice that it was interrupted. For system calls, it's very similar for kernel's point of view, and it saves state into trap frame as well as for interrupts. But this time, application voluntarily calls exception traps, and it wants some information, or it wants to do something for kernel, and when it comes back from kernel, it sees some things change, like some memory areas are written, or it was read by kernel, or some registers has changed for returning values. So it's basically a trap. And while entering kernel, a kernel does the things for application, and it modifies it's not written. It modifies trap frame struct and just return back to application. So kernel has to change trap frame, and it also saves some state on stack too. So Valgrind has to simulate this, and it uses system call both for emulate both for application debug target, and it also uses system call for itself. And Berglund does not rely on host libc for some reasons, including to avoid symbol conflicts. I don't know all of them, but it does not use libc codes, but instead they has its own system call wrappers, and uses it. For example, just open a debug target file, read its elf headers, something like that. So basically, Valgrind simulates what kernel does for system call. The difference is that, as I said, Valgrind interrupts client text, and it mapped in the process, and it reads instructions and execute one by one. And registers are also allocated in the same process address space. So basically, it's most of system calls are just passed to real kernel. For example, if client wants to read some file, Berglund, of course, has to read some file descriptor, some data from kernel. Otherwise, it cannot pass that data back to client. And yes, basically, it's just modified reads or system call. And when Valgrind meets system call instructions, it checks machine state struct and its contents has arguments to system calls, so it can know what debug target want to pass to kernel as arguments. And of course, later it has to return values as system call return values via registers. So Berglund fills client machine state and choose write registers and fills it. And internally, it actually calls system call against kernel. And those wrappers are written. Valgrind has its own wrappers to call real system calls, because when Berglund sees client system call instructions, it's running Berglund code. It's Berglund kernel. But when Berglund executes real system call, it's for client debug target. So it has to carefully swap context. And when it actually calls real system call, it carefully reads register values from client machine state structure and move them into real registers and just call it. And after that, carefully restores register values back into machine state. Okay. So you have to carefully implement these assembly wrappers. I'm sorry for just include code, but it's basically you see there is sigmask. It has to block all signals during calling system call. Signal has many problems, and I will explain later. But it's basically Valgrind polls signals. It does not accept signals, and it wants to control all signals explicitly. So it basically blocks all signals during system call. Then later, this instructions is just looking into structures and assign into real register to pass them as arguments. And you have to set a system call number 2, of course. And this is a real system call. And later you have to put back registers into some structure and against restore signal mask, and done. Berglund has many where it can have hooks for all system calls. Berglund tracks memory read-write when memory is written or it's read. And it's easy for user programs, but it has no knowledge. It cannot know it has no knowledge what memory is written or read by kernel. So if without this knowledge, Berglund, if some memory is written by kernel in system call, and a user application try to read those memories, if without this knowledge, Berglund mistakenly reports that you are touching initialized memory, like that. So we have to teach all this information for all system calls. This is a little messy, and if kernel these system calls conditionally read or write, it's much more complicated, and it's impossible to maintain perfectly. Okay, next exactbe. When, as I said, when Valgrind executes debug target program, what it does is actually exactbe. It has to create initial process image and execute. So Berglund calls this operation init image, and it calls just image. And sorry. I don't. So initial process image is something like it's just process memory contents and initial registers and per process resources, which is stored in kernel as struct process in OpenBSD and struct. Depending on operating systems, there are many per process resources. So initial memory image has text, of course, and database BSS areas, which can be mapped by parsing elf program header. It has road entries. So for kernels, kernel has elf header parser in kernel, and it parses and look for those road entries, and internally map those vnode areas files into process address space. And the initial process image has a stack with arguments and environments and auxiliary information for dynamic linker, which these are metadata for processes to initialize programs to set up things for our main function. These are done by start code in user run. So there is a hidden ABI. There is hidden promises between kernel exec and start code in user run. Of course, there are registers which are used to pass parameters from kernel to start code, like this. So exactbe. So along this development, I had to understand exactbe function in kernel to simulate it on Valgrind, and I had to figure out which part I need and which part I don't need. So, but when I looked at the exactbe function in NetBSD, at the time it was wrong function, and it has, I had no idea which is needed, and dependency was unable to understand, so I could not figure out, I could not help splitting those long functions into small functions. It was fun. And another problem is all BSDs have slightly different ABIs for these. For application, exactbe of course is standard function, but as I said, it has a hidden ABI, hidden promise from kernel, between kernel and the start code, and what content to put on stack and what values in registers. They are not documented and slightly different among BSDs, and those differences I could not see any benefit one over one. They are just different for no reason, so it's strange. So to initialize a process, you had to fill these things. And typically, traditional BSD has on stack argc and argv and environment and AUX info for mainly a dynamic linker and those strings on stack. And of course, initial stack pointer has to point on top of those exec arguments. But as I said, there are huge difference between among BSDs, where to put stack and alignment, and how to pass arguments. For example, NetBSD has PS strings, which is just a little duplicate of pointers connected to argv and env and argc and count of env strings in one struct, and try to pass address of that via registers, which is, I'm not sure it's helpful, but not really useful. OpenBSD doesn't have that. So I had to adjust all those differences and carefully implement it. Otherwise, things doesn't work. And Berglund has to simulate this exactbe precisely. So again, it has Berglund runs a target debug program within the same process address space, and it has a client machine state register content in its memory space. So basically, it sets content in machine state structure, and it has to fill a client stock exactly the target device, a target process expects. Okay, 15 minutes. Signal. Signal is interesting thing, and I think all of you like signal. For me, it was, I have little knowledge about signal, and I didn't read any signal code in kernel, but I had to understand it, and now I like it. And yes, signal is basically same as system call. It's basically a trap, and for application, it looks like a function. If you press ask kernel be a sig action function, and ask kernel just call this function when signal is triggered. But from kernel's point of view, it's a kind of trap, and just yes. Sorry. It's special in some ways for kernel. Basically, kernel just restores application user and state when it's triggered by hardware interrupt. Except one exception was system call, and another exception was exec, which these are few exceptions when a kernel transfers user and which is just not restoring original context. And when this is about signal handler in user space. So when application asks kernel to call signal handlers instead of just exit processes, kernel has to set up context temporarily to call those clients signal handler function. This is done by executing a small code called signal trampoline. It's just only some instructions just to call signal handler and just return back to kernel. And signal trampoline expects some arguments from kernel, which is put on stack. And from application's point of view, it's just called just this signal handler function is called, and when it exits, original context is just restored. But during that, kernel has to save context, the original context, and execute 100, and again restore the original context. And the original context are typically saved onto the stack. Otherwise, kernel has no space to save that information. And of course, there are hidden ABI promises between signal handlers and kernel, and they are slightly different among BSDs. This is a trampoline code for our FreeBSD AMD64, which is in kernel, and only a few lines of assembly code, and these are copied into user space when executing signal handler. And you see this expects that actual signal handler address is stored on top of a stack. This is ABI. For OpenBSD, also has signal code in kernel and copies those code onto a client user space stack. And this one expects signal handler address in RAX register, which is different from FreeBSD. NetBSD is slightly different and special that in that it implements signal trampoline in userland for some reason. So this code is this fragment of code is called after signal handler exits. This is put carefully and as a return code of signal handler. Slightly different. Okay. Berglund has a unique strategy to handle signal for clients. Basically, it blocks all signals and pulls signals when it wants to, using a SIG-weight info system call. But you cannot block synchronous signals like segmentation fault. And how it works internally is very difficult. I will explain later. And trampoline, Valgrind has no notion to copy executable code at runtime. It may be possible, but FreeBSD people decided to avoid that and provide a trampoline from user. This is like how NetBSD does. But it works. And when returning back to kernel, userland cannot really return back to kernel. It just calls a fake return system call, SIG return system call, and it's only handled by Berglund. So this a bit simplified. You can basically Berglund has to simulate what kernel does, and okay, this is for all synchronous signals like segmentation fault. And this is very, very difficult to handle. And actually, Valgrind, as I said, Berglund basically blocks all signals if possible, and it receives other signals like synchronous, and those conditions are stable. Sorry, static. When application want to block some synchronous signals, Berglund Berglund has it remembers those signal masks internally, but still configure kernel in the static manner. So basically, Berglund has static information internally. And when Berglund receives a synchronous signal while doing execution, it jumps to where? Sorry. Okay. Okay. You can read this in this paper later, unpublished. But basically, it handles receives signal and long jump out of that context, and try to the executing scheduler from there, and actually execute a client signal handler from within scheduler. Okay. So I had just 1 minute. I had to change base operating system to make Berglund work. One needs system control, sys control.
We really have to wrap up now. We're getting into the
Okay, sorry. Okay, 1 minute to summarize. I could manage to make Berglund work, almost work, but I still need a lot of work to support all system calls. Berglund is good for users, and it's good as far as it works for users, but internally for developers, it needs a lot of work and to maintain.